With currently existing statistics, you always analyze a single dataset, allowing you to detect patterns in this dataset. Or, more specifically, it allows you to determine the patterns and rules that apply to the specific setting from which the data was collected. But honestly, knowing what happened in this one specific scenario has very limited value and isn't much use to anyone. What we truly need is a set of universal rules, principles that extend beyond a single dataset and apply to all humans in all settings. Only then can we achieve a true understanding of human behavior. But how could we find such universal rules? Well, with conventional statistics that analyzes the data from just a single study, finding truly universal rules is impossible. There is simply no way to determine whether a rule applies universally by testing it in only one specific scenario. No, the only way to establish a rule's universal validity is by checking for its existence across a wide range of different environments. This is exactly what Tree of Knowledge does. It makes use of the fact that there are thousands of datasets openly available that contain information about people in a diverse range of circumstances. By evaluating and refining rules across hundreds of these datasets, Tree of Knowledge identifies patterns that hold true across all contexts, allowing us to uncover genuinely universal rules. The ability to find universally valid rules is just one of many game-changing advantages of this new approach to statistics, which we believe will fundamentally change the future of social sciences. We'll look at the other advantages later. But first, how does this new approach actually work? Remember how a statistical analysis allows researchers to extract insights from a dataset. Let's represent the statistical analysis as a plant and the insights as its leaves. Over the years, many social scientists have analysed many different datasets this way, giving us many different insights. Unfortunately, the replication crisis has shown us that insights that are based on only a single dataset are not very robust. A meta-analysis is more robust than a simple model, as it combines the learnings from multiple datasets. Unfortunately, however, the included datasets have to come from extremely similar studies. This severely limits the number of datasets that can be included and makes it likely for there to be common biases and other problems with the data. Meta-analyses, therefore, aren't particularly robust either. In this video, I would like to present to you the new type of model that is used by the statistics platform Tree of Knowledge. Tree of Knowledge uses a completely new approach to statistical modeling that combines the learnings from very different datasets. The included datasets are not even limited to studies. You can also include any of the millions of observational datasets that are openly available. As more and more datasets are added to Tree of Knowledge, this model will continue to grow in robustness, accuracy, and scope. But how does it work? How can a single model be trained on datasets covering areas as diverse as people's voting behaviour, business deals, sports, and much more? Well, the idea is inspired by physics. At the core of physics models are fundamental agents for generic objects such as solids, fluids, and light. These fundamental agents are very powerful. The agent for modelling solids can, for example, be used to exactly model any mechanical system. To model the cogwheels, for example, an engineer will make a 3D model of these cogwheels out of solids. We can automatically simulate this system by letting each cog simply follow the behaviour rules for solids. We can use the same solid agent for accurately simulating arches, with each stone being an agent. Same for pendulums. Any mechanical system can be accurately modelled by just bringing solid agents into the right shape and configuration. Tree of Knowledge also uses such fundamental agents. These are the fundamental agents for modelling humans, countries, companies, or other actors in social systems. You can model a system with the person agent by putting the agents into the right configuration and specifying details such as the people's age and character. Using the same fundamental agent, you can also model people queuing. Really, any social system can be modeled by putting these fundamental agents into the right configuration. This way, we have a single model, the behavior rules of the person agent, which is used for modeling all these different datasets. Let's look at the agents in more detail. There is a crucial difference between the agents in social systems and to the agents in physical systems. While we know the exact behavior rules of the physics agents, we do not know the behavior rules for the social agents. Well, in some cases, we know the exact rules. For example, we know that the age of a person increases by 1 each year. And we know how to calculate a country's population as a function of its birth rate, death rate, and immigration. For the other rules, which we are not sure about, we have statistical functions. Such a statistical function, say the function for calculating someone's extroversion, could depend on any of the person's own attributes, other people's attributes, or even events from the past. Once we specify such a function, Tree of Knowledge will automatically fit this function to the data from the studies using Bayesian inference. And it is also fitted to the observational datasets using simulation-based inference. Then, Bayesian statistics is used to combine the parameter estimates from all the different datasets. And as a final step, it is also used to evaluate the fully fitted function. Concerning the evaluation of statistical functions, the statistical function we just now trained was just a guess. Let's say we guessed that extroversion depends on someone's energy levels, their familiarity with the surrounding people, and the unknown weight parameters which we just now learned. In truth, we don't know if this function is correct. Extroversion might depend on very different things. With Tree of Knowledge, it is easy to exchange our guess with a new function that depends on different variables and have the new function automatically trained and evaluated on all datasets. Here again, the software first automatically fits the new function on all datasets. Then it checks whether the person agent with the new fitted rule now produces more accurate models. In other words, it checks whether the new agent with the new rule does a better job at mimicking the behavior of the real people captured in all these different datasets. If it does a better job, we keep it. As we continue to try out different rules, we will find increasingly good ones. We can also try changing sets of rules. At the end, we will have found the best possible set of behavior rules for people. This is an incredibly powerful thing. Some people consider it the holy grail of social sciences. The person agent has been used to correctly model people across hundreds of different settings. It has therefore been proven to correctly simulate people in any circumstance. In short, we now have an accurate fundamental theory of human behavior. We can go through a similar process to find the best possible behavior rules for the other social agents too. To appreciate the power of these fundamental theories, let's once again compare this to physics. Newton rose to fame by discovering the correct behavior rules of the solid agent. Since then, the agent with these rules has been shown to accurately model mechanical objects in hundreds of different circumstances. The agent's consistent accuracy across diverse settings inspires our unwavering trust in these laws of nature. This trust, due to repeated confirmation, is also what gives physics its renown. By showing the agent to behave correctly across this wide range of scenarios, it has been proven to be universally applicable. It can therefore not only be used to make accurate simulations of already known systems, but can also be used to model completely new and unknown systems. Structural engineers, for example, use the solid agent to make an exact model of all the building's structural components and then simulate various kinds of earthquakes on this model. These simulations capture the exact dynamics of every structural element and allows the engineer to get a detailed and complete understanding of their design. The fundamental physics agents aren't limited to modeling buildings. The same agents are also used to model systems in all areas of engineering. This ability to fully understand previously unseen systems has completely changed the world. Most of the modern technology we rely on every day couldn't have been created without it. In short, the physics agents have revolutionized mechanical engineering. We believe that the social agents could revolutionize social engineering in the same way. As mentioned before, these agents have also been shown to perform accurately in many diverse scenarios, allowing us to model not only already studied social systems, but also completely new ones. With the agents we optimized earlier, we can accurately model and simulate any social system. We could, for example, predict what would happen if a certain law was introduced, or what would happen if a new bus lane opened up, or how countries' economies and international relations might change over time. With the fundamental agents, researchers get the ability to accurately simulate absolutely any social system by just placing the social agents that make up the system in the right configuration and specifying their details, such as their age, character, etc. With conventional statistical models, on the other hand, we can only model types of systems that have been observed in the real world and for which we have an existing dataset. The ability to accurately simulate completely new, previously unseen systems is very powerful. It allows researchers and advisors to quickly test and iterate through different social system designs without having to make a single experiment. In short, the ability to accurately simulate mechanical systems has been the key to creating practically all modern technology. We believe that the accurate simulations of social systems could lead to similarly advanced engineering, giving us, for example, more efficient laws, institutions, and welfare. There is only one remaining problem. For the physics agents, we know that their behavior rules are 100% accurate. For the human agent, we might not be able to reach this level of accuracy. Even after all the optimizing and improving of behavior rules, we might only end up with a 94% accuracy. 94% is quite good, but it still leaves us a little uneasy about how much we can trust the predictions made by the simulations. Fortunately, this problem has been solved. Instead of just running a single simulation, the software runs thousands of possible simulations. Each simulation weighted with the probability of reality unfolding this way. So, for any simulation metric, say the happiness of person 1, we'll have a distribution of simulation outcomes coming from the different simulations. In other words, we can now determine the probability of any real-world outcome. The distribution of outcomes accurately reflects the true uncertainty, which we have due to our lack of understanding and lack of data. The underlying Bayesian framework makes it possible. It captures the uncertainty we have due to lack of data and understanding in the parameters of the agent's rules, and accurately propagates this uncertainty through any simulation. So, as we get more data and the agent's rules improve, the uncertainties in the parameters decrease, and as a consequence, the uncertainty in the simulations decreases as well. In short, these probabilistic simulations allow us to test social system designs with the same powerful methods as engineers use, with the one difference being that every prediction carries a statistically rigorous uncertainty, an uncertainty that diminishes as tree of knowledge grows. So, how does this new approach compare to the current practice? What do we gain by moving away from individual analyses to an agent-based fundamental theory? As you might imagine, the differences are profound. Instead of having a confusing collection of disjoint and partially contradictory analyses, we get a single, cohesive theory. The theory that best fits to all datasets. And the individual analyses are all based on only a single dataset, making them very fragile and not very trustworthy. Our agent, on the other hand, is trained and evaluated on hundreds of datasets, making it a lot more proven and robust, and much more accurate. Also, having been shown to be valid in this wide range of different datasets makes it a universally valid theory. Furthermore, the agent allows us to create detailed micro-simulations that capture all the mechanisms and allow us to get a detailed and complete understanding of the modeled system, as opposed to conventional statistical models which only reveal the broad trends. And unlike traditional statistical analyses, which can teach us only about systems for which we already have data, the agent allows us to predict and understand the behavior of absolutely any system, making it vastly more powerful and useful. These advantages of the new theory-building approach are not just minor improvements, they are game changers. We are convinced that the new approach will allow the social sciences to evolve into an exact quantitative science. As time goes by and new systems are modelled, the accuracy, scope, and robustness of Tree of Knowledge will continue to grow. Check out the following videos for a more in-depth explanation of the advantages of the new approach.